Hello! In this video, we will discuss the basics of electricity, the hydraulic analogy, and the conservation of energy, as well as the generation of power. So we know from chemistry and high school and physics that an atom has three basic parts: the neutron, the proton, and the electron. For our purposes, the electron is bar none the most important. And there's a specific number of electrons that we really like. 6.022 times 10 to the 23rd electrons is 1 coulomb. And a coulomb, of course, is the unit of charge. So coulombs also have the abbreviation C and measure charge. Now, if we have some coulombs, some electrons moving across a copper wire, if we select some arbitrary point on that wire and 1 coulomb of electrons, or 1 coulomb of charge moves across that arbitrary point in 1 second, we have what's called an ampere. So 1 coulomb per second is equal to amperes. Amps and amperes, of course, are the same thing. We're just lazy engineers, so we take all the shortcuts we can. This current, it doesn't happen spontaneously, though. We need to have a force, something to drive it. And that force is called voltage. And voltage is a relative measurement. So from the positive to the negative is where our current is going to go. However, let's say we've got 14,001 volts V on this side and 14,000 volts over here. We still have a voltage difference of 1 volt. And that's what's important, is the difference between the two. Now if we do have 1 volt, and we have 1 amp, and they move across, if that current moves at 1 volt in 1 second, we generate a joule of energy, 1 joule. The third component is resistance. Resistance is kind of the backward force, or the friction, I guess you could think of it as, of these electrons moving down this conductor. And resistance has units ohms and is given by the symbol omega. So ohms, named after Georg Ohm. And the relationship between volts, current, and resistance is given by Ohm's law. Volts V is equal to current I times resistance R. So if we have a constant number of volts, constant electric potential difference, and we increase our resistance, our current, of course, is going to go down, and vice versa. The hydraulic analogy is another way to think about these. So we have, say, 2 buckets full of water. And we know that the water is going to flow down that pipe into the other bucket. And that flow is going to be a function of the pressure difference between the two, right? So we've got this pressure difference between 2 buckets. We have a flow. Well, kind of put it on the nose here, and we can say, well, the flow is going to be current. And the pressure then will be voltage. And if we remember, as I was just saying, that V equals IR, the pressure, if it remains constant, is just going to be a function of the current times the resistance. if we say put in a valve here, which looks like a little bow tie in the mechanical world, you can kind of picture that valve opening and closing so that it looks like the rest of the pipe, or it's fully closed in its bow tie form. If we've got water flowing into this, or current even, is there going to be a lot of resistance? Yeah, you betcha. Barely any current's going to be able to get through. If it's a really good valve, none will. So our resistance is really high, therefore flow or current is really low. Similarly, when that valve opens up, all we have is just a wide open pipe. Resistance is going to be low, current will be high, voltage is going to stay the same. Note here too that volume is analogous to charge, so that's not a tidbit we'll be using much in this class. It is important to know. Finally, we have power. Power is related to energy, and energy is always conserved. You can't create or destroy energy. You can convert it to matter and back and forth, but we know that relationship is governed by the infamous equation E equals mc squared. But for our purposes, we can just say that energy is always going to be conserved. And this energy comes in many different forms: kinetic energy, potential energy, radiant energy from light, chemical energy, electric energy, you name it. And the golden rule here, that energy is always conserved, when physicists observe that it's being broken, they invent new types of energy, like dark energy, which is supposed to explain why the universe is still expanding. But electric energy is the one we're really concerned with. And we know electric energy already. 1 volt times 1 volt times 1 amp times 1 second is equal to a joule energy. And more generally, we can write this as work or energy is equal to the integral of voltage times current times our time slice, dt, our change in time. And power then, well, it's easy. We know power is a rate of work, how much work is instantaneously being generated or released. So P, power, is equal to the derivative of work, the time rate of change of work. And if we take a derivative of our integral up above, all we get is V times I. We can sub this in even, right? So we can say work is just the integral of power. Voila! And that's all for this video. Thank you.